Hello YouTube, I'm back for another episode of Using Mathematica. Alright, so what I have open here is a PDF booklet that I am in the process of creating. It's called a YouTube course in Mathematica. Okay, so let me just walk you through it. So the things that I have already done are in the beginning. So far I'm up to this second chapter, the basics. This is what I've already done, and the next part we will do is mathematical induction. So let's move on over to that, which in this is on page 9, and let's begin. But first of all, I'll say that this is on my website, and there will be a link in the description below. Okay, so let's have a look at this. First of all, we are going to construct a list of the values of n squared plus 5 for n going from 1 to 25. Alright, so let's just do this. So we just put in the expression n squared plus 5, and I want to tabulate over that. Tabulate that as n goes from 1 to 25. Comma, and the curly brackets go in here. Now it's over n, and I put in the start as 1 up to 25, and I end the square bracket. And now shift and enter. We'll execute this. Alright, now we find, since the first square is 1 squared, 1 plus 5 is 6. 2 squared is 4, 4 plus 5 is 9, and so on. Alright, so that's the first question done. Now let's move on and do the second question. Oh, well, there's a bit more. Okay, so this asks to use the mod function to determine whether any of these are divisible by 4. Alright, so first of all, let's call this list S. Now I can put a semicolon in here, and then around that I'll just put mod, and I want to know what the remainders are when you divide by 4. Okay, so I put in comma 4, and now I put in the name of that array, which is S. Okay, so these will be the remainders mod 4. So numbers 0, 1, 2, 3. Those are the possibilities for these remainders. So let's have a look. Alright, so we see 1s and 2s. 1s and 2s. All the way through the list. And now none of those have remainder 0, mod 4, so therefore none of those are divisible by 4. There's a weird lighting effect that's going through my face. So let me see if I can sort that out by moving my lights, adjusting my lights. I reckon that must be the window. So I'll just pause for a second and shut my curtains. Oh, I'm an idiot. It's the cable. Alright, sure. So I moved the cable. It's the audio cable. Righto, back to it. Okay, so where were we? We were working out that none of these numbers are divisible by 4. So you can say, well, I mean, because this is only the numbers from 1 to 25 that were tabulated over. So this means that none of the numbers n squared plus 5 are divisible by 4 for n going from 1 to 25. Alright, so you could in a comment say n squared plus 5 doesn't seem to be divisible by 4. Alright, now that is provable. should be provable that this number is never divisible by 4. Okay, but that is not an exercise for this session. This is a computational exercise on helping you computationally think about things. Okay, so let's now move on to the next question. Alright, so this says, by an exhaustive search, determine whether 7m plus 4 is divisible by 7 for any integer m in the range 0 to 10,000. Okay, well I can just tell you straight away, it's obviously never going to be divisible by 7 for any integer m, right? Because this, when you divide this number by 7, you'll see that it has to have remainder 4, alright? And now, at the same time, I also notice that this is a little too small for you to see. So let's zoom in on that. I'll take it off the 2-page view. Zoom in. 1 per page. Alright, is that better? Seems like it should be. So I'll open up the Mathematica again. Okay, so I'll quickly do this, an exhaustive search. Alright, so I'll write the expression 7m plus 4, and then you would tabulate that, where m ranges from 1 to 9999, so 9099, and that is over m. Alright, so let's have a look. Alright, that is a long list, right? So let's call it S, semicolon, so that we don't show that. It's in memory now. And let's take mod S, comma 7. Alright, they're all 4, no surprise there. Alright, so if we want to see, are there any other elements in this list other than 4? So to test that, we can just write union. Okay, let's have a look. Shift and enter. So this says that 4 is the only element, the only unique element in this list. Okay, so that tells you that there are no other remainders than 4 for m between 1 and 9999. Okay, but that's obvious. We knew that that was going to work out that way. Nevertheless, it's an okay exercise for beginners. Alright, next question. By an exhaustive search, where a and b are between 0 and 50, determine whether it is likely that the following holds. If a, b, c are integers and they satisfy a squared plus b squared equals c squared, then at least one of a and b is even. Alright, there's a hint there, use even Q. Alright, so let's begin this. I'll open up a new cell by pressing enter down here. Alright, and now first of all, what these are, they are Pythagorean triples. Alright, so if you're thinking about right triangles, these refer to right triangles in which the sides of the right triangle are integers. Okay, one famous example is the triangle with sides of length 3, 4, and 5, with 5 being on the hypotenuse. So, first of all, I will want to look for Pythagorean triples. Now, this says for AB between 0 and 50. So we don't need to worry about negative numbers. Now, I want to ask the computer the question, when is a squared plus b squared having a square root, which is an integer, right? So I'll just start with that expression, SQRT, a squared plus b squared. Right, so this is the square root, the positive square root of a squared plus b squared, right, which would normally be c. If a squared plus b squared is c squared. Right, but I also want to know, is this an integer? Okay, so let's call this c. C equals. And I'll put a semicolon, so not to show the output. And now that is the value of c. Okay, so I want to know, is c an integer? So after that I can say integer q, which is asking the question, true or false, is c an integer? Okay, so now that we have that, well, this is still in terms of a and b, right? They're bright blue, it's still in terms of a and b, so shift enter now would not give us anything meaningful. Alright, so what we want to do is make a list tabulating over a and b. Alright, so I will write table in front of the c, table, and then over here I'll put comma and I'll say what I'm tabulating over. So first of all, I want to tabulate over a, going from 1 to 49, right? Because that's what this says, go from 1 to 49, right? And the same for b. b goes from 1 to 49, right? Whoops, no, from 1 to 49, not 149. End the square bracket. All right, let's try this out. This should be something that it will do something now. All right, so let's shift enter and see what we get. False, 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 false. Lots of falses, right? Oh, I see a true. There's a true there, but that doesn't tell me what the Pythagorean triple itself is. All right, so now that we have this, we want to ask a further question, or say what we want to do in the case of true and false. Okay, so now we will modify this and say if. Now put in the square brackets because I am putting it around the question, is this an integer? Okay, so I'll end the square bracket there, and that up arrow tells me I need to say what to do when it is. Alright, so comma, another comma for what to do when it's not the case. Alright, so let's start with the true output. So if this is true, let's put the triple a, b, and c. Right, notice how a and b are like a turquoisey color and c is black. That's because c got stored into memory, whereas a and b are not in memory. They're just things that we're tabulating over. Okay, so now that's what we want to output in the case that we get true, right? In other words, a Pythagorean triple, ABC, will come out in the case true. And what about false? Well, we want to put something that we can later get rid of, something trivial. Let's put 0, 0, 0. Okay, now let's try it and see what we get. Okay, so we have a very long list. That's what we can see here because there are some dots. So it's a very long list. Now we don't want to show more, show all, etc. What we want to do is have a look at what we have here. So we have triples here, but since we're tabulating over two things, it's doing so first over, say, A, and then over B. And so what we want is to get rid of an extra set bracket, right? Because first it does this over A for a fixed B, for example, and then does it for the next B, and so on. Okay, so now we want to just have one list of triples. So to do that, let's call this T, okay, and put a semicolon. And then after that down here we will say, let's choose another letter, W equals, and what I want to do to T is flatten, all right, flatten. This is a command for getting rid of all the set brackets within, right? So remember, set brackets denote an array in Mathematica. Okay, so we will flatten T, and now let's have a look at what's different. Okay, now we have just a list of numbers, but that's not precisely what we want either. So, and you can see, oh, there's 4, 3, 5. Okay, this is going to correspond to one of our Pythagorean triples. So now what we want to do is partition that into triples. All right, so we will write partition, and we'll partition it into threes, right? Partition into threes will give us triples. So let's have a look now. Okay, now we have a long list, and we've gotten rid of a set bracket. So it is in fact a long list of triples with mostly 0, 0, 0. So mostly the cases in which a squared plus b squared was, the square root of that, sorry, was not an integer. So we want to get rid of those, okay? So we'll put a semicolon here, and now we'll pick a new letter. Let's go for y equals, now what I want to do is get rid of those unwanted triples of zeros. So I'll say delete cases. W, and what I want to delete from this list W is triples containing 0, 0, 0. Okay, now let's have a look. Sure, so we see 3, 4, 5. That's probably the most famous Pythagorean triple. 4, 3, 5. Well, I mean, that's just swapping the two sides, you see. And then 5, 12, 13. That's also well known. 6, 8, 10, and so on. So we have a long list of Pythagorean triples that we've generated. Okay, so that's good. Now let's have a look at the question. Now that we have a list of Pythagorean triples, the claim says if we have a Pythagorean triple, then at least one of A and B is even. So now that we have Pythagorean triples, we can test, is one of A or B even? I'll put a semicolon, and I'll create a new letter, Z equals. Now I want to ask questions of the jth element. So what do I want to ask? If. So this is a question. And what do I want to ask? Y, J, the jth element of Y. Okay. Comma, comma. Okay, so what are we asking? Whether or not one of these, the first or the second. So let's say little q equals this. And actually I want to put that before, don't I? Put that before. Little q equals this. Look, I'll get rid of the big Z right now. I'm just writing an expression, thinking about along the way what I'm building. Okay, so q is the jth element. Well, really I want the first element A of the jth element, and then R equals Y J, comma 2, second element. Now this is B, right? So actually let's be smart about it and call these A and B. A and B. Okay, so what are we asking now? If even QA or even QB, then, okay, so we fill in what we want to do, and after the first comma, then we should put A, B, and now, well, we've gotten rid of this, so I'll have to copy and paste this. Now, unfortunately, we're calling on it twice, but oh well. Then A, B, C. Okay, if not, then put 0, 0, 0. Okay, now that we've got this if expression, we again want to tabulate over A and B. Actually, no, we don't. We want to tabulate over J, right? Because J is the jth, corresponds to the jth element of this list Y. Alright, so we're tabulating this over J, and we have to start this up here. The table, and then we go down, after this, comma, and we're tabulating this as j goes from 1 to the length of the array y. Okay, now that should be good. Let's try it out. See what we get. Well, it seems that we don't have any 0, 0, 0. Okay, so maybe instead of putting this, we can just put a 1 and otherwise put a 0, right? Because that'll be easier to see whether or not that's always the case within that list. So look, we have all 1s, right? And if I really wanted to properly ask this question on a longer list, then I could just put union in front of this and see if I only get 1s. Alright, yeah, that's true. So this does seem to be true, right? At least it's true for AB between 0 and 50. That in a Pythagorean triple, A or B is even. One of those. At least one of those is even. Okay, so that's probably enough for this session. So let's end that for now, and I'll see you next time. Thanks for watching.